So now we are ready to calculate the Earth's temperature. We just base on this equation. Incoming shortwave radiation is equal to the outgoing longwave radiation. Yeah, we base on this equation. Yeah, let's do it. First, energy will come from solar. Yeah, we want to ask a question. How much energy is pushed out by the sun per second? This is called the solar luminosity. Yeah, that is a constant flux of energy put out by the sun every second. This number, yeah, 3.9 times 26 power, yeah, watts. That's joule per second. Okay, this is the Y. Next, we want to ask, this energy, the transfer, the going transfer to the far area. Another we call the solar flux density. So that means if this maybe 20 seconds, maybe 2 days. So where this radiation go? So distance, radiance. Yeah, distance. Maybe we use d. That's distance. So there's a ball. There's a sphere. We want to ask the question that's what is the solar energy pass the unit area on that sphere per second? Yeah. We want to know this. This is called the solar flux density. Yeah. Just on that sphere with diameter is d per unit area, how much solar energy pass over per second. We have to know. That's easy. Just use L total energy divided by the sphere area. So that's per unit area. Now is the question. What is the sphere area formula? Yeah, I think you learned this from in your high school, right? Yeah. 4 pi r squared. Yeah. You like a ball, what's the total area? 4 pi r squared. R is the diameter, is the radius of the ball. Yeah. So here, this solar flux density formula should be here. This L, solar luminosity, or the total area on the sphere with radiance is d. Yeah, 4 pi d squared. Yeah. So we can calculate this number. We don't care to somewhere. We care this solar energy, how much reached to the Earth. Yeah. To the Earth. What is d? Yeah. You see the d. The d is the distance between sun and the Earth. Yeah. We know this distance. Yeah. We know the L. Yeah. So we can know how much solar energy reached the Earth. Yeah, at the top of the atmosphere is 1,370 watts per meter square. This is called solar constant. This is a very, very important Earth parameter. Yeah. All our energy comes from this number. Yeah. You have to know this. I will put this in your exam. Yeah. 1,370 watts per meter square. Yeah. That's at the top of atmosphere. Yeah. So we want to calculate its E yin. That's the incoming solar shortwave radiation. Solar constant 1,370 watts per meter square. Received energy from sun only daytime, right? Yeah. Half of Earth's surface. Yeah. So, if there's a half Earth's surface projected to the circle, that area, per meter square per second, energy received from the sun is 1,370, right? If time this total area, shadow area, that is the total solar energy received by the Earth. Pi r squared. That r is the radiance of Earth. Yeah. So we know all these numbers, right? We know the radiance of Earth. Yeah. So we can make calculation. Yin. Okay, solar constant time pi r squared. Told me. So we have problem. This is not correct. What we are missing? Solar energy cannot be totally received. Some of it is reflected, right? Yeah, some energy is reflected. There's albedo. So there's albedo. We have to minus the reflected part. What is the average albedo of the Earth? 0.3. Yeah. So now this formula is right for the total energy received from the solar radiation. Yeah. Okay. We are done for the yin. What's next? E out. What's the equation? E in is equal E out. Yeah. So what is E out? That's energy emitted by the Earth. Yeah. So what radiation law we will use to calculate its E out? Boltzmann law. Yeah. If there's a temperature, that's emits radiation every moment, right? This E out only during the daytime, only during the nighttime. No, any moment from anywhere on the surface of the Earth, the lucid energy. Yeah, everywhere. Everywhere, that means totally sphere, total area of Earth's surface, right? Yeah. What is the total area of Earth's surface? 4 pi r squared, right? So 4 pi r squared per unit area, how much energy get out? Read it. Based on Stephen Boltzmann law, sigma temperature force power. That's per unit area. Time total area of Earth's surface. 4 pi r squared. R is radiance of Earth. We know this. Wow. Now we got E in. We got E out. Yeah. All numbers we know, only one is unknown. What is unknown? Temperature. What are we going to do? We want to know. Yeah. How to know? By the equation. Yeah. One equation, one unknown. That's perfect. We can solve. Yeah. So E in is equal E out. Yeah. So you see, this is E out is equal E in. Yeah. And TE is the Earth's temperature. Yeah. So there's something we see is 4 pi r squared, 4 pi r squared on the both of this equation. We can cancel that, right? Yeah. So we can have this equation sigma T4 squared. Yeah, equal number. Yeah, A is equal 0.3. Yeah. Solar constant is 1370. Yeah. So based on this equation, we can solve this Earth's temperature. The Earth's temperature is minus 18 degrees C. Too cold. Yeah, that's too. Yeah. So what is the current Earth's temperature? Yeah, we know this, right? Yeah. Earth's temperature, average Earth temperature, 15 degrees C. Yeah, 15 degrees. Why they are different? Why they are different? Yeah, because when we calculated this Earth temperature, we did not consider it atmosphere. Our calculation is without atmosphere. That's minus 18 degrees C. If with atmosphere, average temperature is 15 degrees C. Hey, what's the difference between them? Between with atmosphere and without atmosphere? Yeah, 33 degrees C. Totally 33 degrees C. What's this? This is caused by atmosphere, by greenhouse gases. This is greenhouse effect. Total greenhouse effect is 33 degrees C. You have to know this. It's a basic knowledge for the Earth. Yeah. So we ask question, what causes this 33 degrees C difference? Nitrogen? Oxygen? No. Nitrogen is 78% in the air. Oxygen 21% in the air. But not caused by them. By what? Greenhouse gases. Yeah. Yeah. By the water vapor. By the CO2. Yeah. Trace gases. Because water vapor is a long wave radiation water vapor can absorb them, then re-emit, then keep the energy in the atmosphere. Yeah, so that's the C of X is the wavelength radiation, radiation from the solar. Yeah, so 50% are visible. Yeah, you see here is the ultraviolet radiation visible, and you're right. This is spectrum of electromagnetic radiation, right? Where the solar radiation here, lambda max is 0.5 micrometers, whereas the Earth radiation, lambda max is 10 micrometers. Yeah, incoming solar radiation in this range of the spectrum. Outgoing long-wave radiation in this focus on located here, the wavelength. Yeah. Water vapor. Water vapor is not black body radiation. It's selected radiation. Yeah. And this short wavelength, this water vapor said, oh, no, I don't want it. Go. Yeah. And this wavelength, water vapor like it. Oh, I want it. And here, they don't want it. And here, want it. And here, don't want it. So, water vapor is a selected absorber. Discrimination. Yeah. So, yeah, you see the water vapor. Water vapor is here in the air. Yeah. So here, long wave radiation, they want to catch up. And here, they want to catch up. Yeah. Even this solar radiation at this wavelength, they also want it. Yeah. So this is water vapor. How about CO2? Yeah. CO2 only 2 peaks. And here, they don't want it. Go. I don't want it. And this peak, yes, I want it. I like it. And here, no. Here, yes. Here, no. Yeah. So, selective. CO2 concentration, CO2 is also selective. Yeah. So, but not much like water vapor. So then we talk about water vapor is the most abundant greenhouse gases. Water vapor only second abundant greenhouse gases. How about ozone? Oh, ozone only 1 peak. That's a greenhouse, not very important. Contribution is so small. However, in the ultraviolet radiation, they all want it. Yeah. So that is ozone. Yeah. So the Earth's radiation only can be emitted to the space through this window. This is called the atmospheric window. Yeah. So this is physics for greenhouse gases. This is science. Yeah, some people don't believe this greenhouse effect. Yeah. You put more greenhouse in the air, so then just like you wear more layers. Yeah, keeping your body warmer. Yeah, that's right. Yeah. So this greenhouse effect. Total greenhouse warming 33 degrees C. What contribution? How much contribute from water vapor? How much contribute from CO2? Yeah, 31 degrees C from water vapor. Greenhouse is not bad. Greenhouse is good for our human being. So there's the greenhouse effect. So our is temperature comfortable, not too cold. Yeah. So then just less than 2 degrees C from CO2 contribution. Yeah. Now the question, what vapor contributes this greenhouse effect warming so much? Why we don't care? CO2 just contributes less than 2 degrees C. Why we care so much? Why? Yeah. So this is the question. Why we don't care about the water vapor? We care CO2. Tell me the reason. Oh, is more water vapor in the air. What would happen? Clouds, rain, storm, they will get out of the air, right? We don't need to worry. 7 days, 10 days, the rain. 7 days, 10 days, rain again. So if more water vapor in the air, they will condense into the liquid water, then we become rain. Get out of the air. So we don't need to worry about the water vapor, right? How about CO2? CO2 in the air, if you want to remove, need a few hundred, you need more than 100 years. That is a problem. Yeah. Here, we calculate Earth's temperature by the equilibrium, radiative equilibrium. Incoming solar radiation is equal of the going radiation, right? However, on a different latitude, this net radiation is not zero, is not radiative equilibrium. So you see the red curve is incoming solar radiation. You see the blue curve is outgoing radiation. Yeah. So at a low latitude, equator, tropic, subtropic, this net radiation is positive. Positive, that means temperature going up. That means hot. That means more energy accumulate in the tropic, subtropic, low latitude. However, at the high latitude, you see, yeah, incoming radiation is much less than outgoing. Yeah, so that net radiation is negative. That's why at the high latitude it's cold because net radiation is negative. So energy is transferred from hot to the cold, from the tropic to the high latitude, right? Yeah. So then you see jet stream